And we are going to look at the yield criteria for ductile material. So it's very common. So there are two. Okay, there are two commonly used. Commonly used yield criteria for ductile material. Okay, so before I go on, so the definition of the ductile material, okay, is usually when the stress yield is so much smaller than the stress ultimate strength. Okay, so that is our definition for ductile material. Okay, so there are two very commonly used, and the first one is known as the maximum shear stress criteria. Okay, so this is most commonly used. And another name, you'll see that the name appear as Tresca criteria. Now, how I remember Tresca, the shearing stress is tau, right? So Tresca rather than T, I spell as Tresca. So whenever I see Tresca, I know it's shear. That's how I remember, okay? And then the next one that is very commonly used is the maximum distortion energy criteria. And this is commonly known as the Vomesis criteria. And I'll show you the difference. Okay, so for Tresca criteria, okay, it states that the maximum stress, allowable stress, is equal to the yield divided by 2. So whenever you see stress yield is from experimental data. Are we clear? Okay. And if we're to look at von Mises criteria, they are different. So on von Mises criteria, tau max will be equal to square root of stress yield squared minus by the average stress squared, and the whole thing divided by 3 and surrounded by a square root. Okay. The most important thing to know, okay, the common between Tresca and von Mises criterion are okay. So our is what? Okay, is must use 3D mole circle during analysis. Okay, that's why you guys saw the example before, the one that we took 2 hours to finish off. I insist that you all draw 3D mole circle. Okay, you see, okay. So I don't have time to go into von Mises, so I'm just going to teach one. I because I have 2 more big examples to show you, and I need time to show you. Okay. So if we were to now focus on Tresca criteria, right? It states that tau max is equal to stress yield divided by 2. As mentioned before, stress yield is from experimental work. And another thing that he assumed, so Tresca assumed that the yield strength in tension or compression are equal. Okay, so indirectly, I've introduced you to Tresca criteria in the previous example. As you can see over here, right? We realize that stress mean is equal to minus 275, yet I use 345. Why I use 345? Because over here, the yield strength I only have in what? In tension. I don't have any value in compression. So when we assume that the yield strength in tensile and compression are equal, we are already using Tresca criteria. Von Mises also do the same. Are we clear? Okay, so I'm going to copy this table. Okay, and we are going to look at the yield criteria now. Okay. So let's say now you are given this table, okay, and you want to find the shear stress, right? You're given this table, and you were told, or you are told by your supervisor or your chief engineer, can you calculate the shear stress for me? So we know, right? You don't have any shear stress value over here, right? You have nothing, right? You only have one, which is 145, right? So let's see if we use the ASTM A36, and from stress yield, we know that it is what? It is at 250 megapascal. And we happen to be lucky enough, right? The shear yield is equal to 145 megapascal. If we were to apply Tresca criteria, right? which states that the stress max is equal to stress U divided by 2, right? So this will be equal to stress max will be equal to 250 divided by 2. This will be equal to 125 megapascal. You can use Tresca criteria and say, hey, I'm going to assume to be 125 because 125 and 145, you're not that far away, right? You're more conservative, right? So what I'm trying to tell you is this. If we were to calculate, now we have ASTM, right? A709, okay? And we know that the yield is 345 megapascal. And you don't have time to do tests, or the test is just too expensive. You can use Tresca criteria to specify this will be equal to 345 divided by 2. Okay, so 345 divided by 2 is equal to 172.5 megapascal. Right? So whenever you do anything like this, where you don't have value and you calculate, you have to state, I'm assuming that the material will obey Tresca criteria. Okay? Rather than waiting for tests to be done. Okay, sometimes some of these tests, this test is not like going to Walmart to pick up a bag of chips. Okay, you have to prepare your samples, you have to do the test. Sometimes it can be costly, and you have to wait. Okay, it can take you 2 to 3 months. When that's the case, 2 to 3 months just way too long. You can make this assumption. Are we clear? It's just time. Okay, so that's where we start using Tresca criteria. Okay, now uh, we're next going to look at this root formula, and we are going to look at 3D mole circle. Okay, we're going to look at 3D mole circle now. Okay, so now based on 3D mole circle, okay, and structure analysis, we know that the maximum stress is equal to stress max divided by 2. And I'm going to call this our equation 1. Okay. Now, stress max is from structure analysis. Remember the previous example, we calculate stress max, yes or no, right? Now, equation 1 is only true if we have the condition where stress mean is equal to what? 0. Okay, I repeat again, stress mean is equal to 0. Okay, so now let's look at one typical example, okay, or one stress state. Or I'm going to write like equation number 1, right, is when one of the principal stresses is equal to 0. Okay, and the other two principal stresses are either both positive or negative. Okay. So let's look at one situation now. Okay, let's look at one situation. So this is based on 3D mold circle, right? So if we have an element looking like this, and then you have stress X, stress Y, and then you have your shear XY, okay, shear XY is equal to shear YX, okay? And then